let's go now. I mean, I will go into the deep learning basics. Why I go into this? There is another full set of slides that they basically do a full picture of shallow learning. So there you will see anything. Let's say you will see most of the traditional supervised learning approaches. You will see quite a lot for clustering, clustering also on big data. You will see things about ensemble learning. So if you're new to machine learning in general, please also go to that. There's slides at number 2. But I will go into deep learning because, as I was saying, today if you're doing machine learning, deep learning is something that it's interesting to explore. It has lots of, let's say, advantages and limitations, as we have seen. But I think it's good that we grasp at least the basics to then jump into other domains. Okay, so inside deep learning, we will focus on one of the, let's say, big game changers that it's about the convolutional neural networks. So, no muted. Okay, yes, let's go into it. So basically, a bit of history on learning. So basically, learning or deep learning, it's about neural networks. And neural networks it started a really long time ago. So the whole idea of neural networks was to try to mimic the way that we think our brain works. And we think that there are neurons and that these neurons, they are some neurons connected to other neurons, and that those neurons, when they are connected, they have some sort of, let's say, what we call some kind of weights or some way to connect that activate them for doing some tasks, but for doing other tasks, other neurons that are connected some other ways, they activate in a different manner. And this led to this idea of having these artificial neural networks. So in the 60s, there was the most popular neural network till today, that is the perceptron. The perceptron is the standard, this feed-forward 3 layers neural network, where you have an input layer that basically you put the inputs, there is a hidden layer in the middle, there is an output layer that gives you the outputs, and then you just connect each layer, all the neurons of each layer to the other layer, and so on. In the 90s, there was, let's say, the first, let's say, revolutions or let's say, big ideas that at the end help in making deep learning what it is today, that it's the concept of backpropagation, actually how to train neural networks in some kind of efficient manner. Boltzmann machines that actually we realized that when those models were too complex to train, there were some ways to actually train them to make it feasible. What happened is that this perceptron, these simple neural networks, we were able to train them and to perform well. But when there were many parameters to set, we were not able actually to do it. The models were just failing. You were trying to basically train them, and the models were going to local minima. The features were, the weights between connections were getting nowhere. Okay. Then, of course, there were let's say in the also 90s. Let's say the convolutional neural networks are not new; they are older, but they were not that powerful at that time because the lack of big data and how to really train these deep architectures. In around 2006, we got the term deep learning was coined. So we have you know that recently there was this Turing Award for what they are called the parents of deep learning, that it's Hinton, LeCun, and I got lost. But basically, 3 researchers that actually came up is basically one professor, that is Hinton, and 2 of its students, Bengio and LeCun. So they were actually working on this field. And from there on, everything accelerated at a super speed. So 2009, we got the net. On top of that, we got the first super models. There's AlexNet that basically changed everything, because using convolutional networks, they managed to strongly reduce the error in image classification. Then we got generative models. Nowadays, we got, let's say, the AlphaGo, AlphaZero. capsule networks, and something that is revolutionizing everything now, that is the transformers. So I will try to show you later on a bit of all these things. But now, what is deep learning at the end of the day? This simple neural network is what I was showing you, the perceptron. And for neural networks, what it's very interesting is that in the theory, there is actually a theorem that actually basically tells that a neural network is a function that can approximate any function that you might think of. So neural networks are universal approximators. And this is something very powerful in the sense that it means that whatever kind of function that can be described by input and output data, even if you don't have access to the real function, you can approximate with a specific neural network. What they prove is that a feed-forward network using a single layer, so basically what I'm showing you there, can actually approximate any function that you might think of. The problem is that in order to approximate any function, it has to, let's say, be very expressive. Being expressive is that it has to have many parameters to set. And what happens in the practice is that what might happen to approximate any function is that the hidden layer, this layer that is in the middle, will have to grow too much in order to have this kind of super expressive power so that it can approximate any function. And this, in the practice, is unfeasible. So the idea is what they came up is saying, okay, if a neural network can approximate anything, and the problem is that I cannot just grow the hidden layer infinity because it will not be feasible, why not extending and making the architecture deeper? So why not having more of these intermediate layers in the neural network? And that was just and the magic of what we have as deep learning, just having deep architectures. We go to that into a minute. But just to compare, when we think about the comparison about deep learning and the human brain actually it's completely different from whatever we think about artificial and neural networks. It doesn't work like what we think about neural networks, and it's by far, let's say, huge bigger than what we normally see. So here, this is a kind of picture that shows something of 3% of the human brain neurons and something like whatever 0.00001 of the neural synapses. So our brain, it's a full mesh of billions of these small tiny elements that they have lots of capacities in the middle. So the whole thing is that even though we originally created neural networks trying to mimic the brain, they were completely different from that. This is very clear nowadays. So just for you to have the overall idea. So as I was saying, deep learning, the overall idea is instead of having one single layer, let's put many layers in the middle, and this will improve the expressiveness power of the neural network, and like that, we will be able to solve this kind of universal approximation problem. The interesting thing is that by having many of these intermediate layers, these neural networks by default, they work at a sort of building different hierarchies of data. Why is that? Is that basically here, imagine at each layer here, imagine that you are using, let's say, in any kind of model, you can always think that each of these layers is like encoding, yes, the data that comes in the input into some different code at the output, right? And the idea here is that each of these layers, actually, if you think as a simple, very, very simple example, there is something that is called an autoencoder. Autoencoder is basically a neural network that, or a model basically that tries to copy at the output exactly what it sees at the input, okay? So if you think about a neural network like this with many layers, and imagine that at each layer you have less and less number of neurons, and you are thinking of this autoencoder that you want to copy at the output what you're seeing at the input, what happens is that each of these layers, at the end of the day, it's, let's say, considering a kind of different hierarchy of the data, because the first layer, we compress the input, that it's all the data, the raw data. Let's imagine a picture, you pass all the pixels. The first layer, we compress it, meaning that we'll detect part of that thing, because if you have less parameters to condense the input data into something at the output, you will have to, let's say, only keep some relevant information. So the first layers will keep some part of the data, whereas the more you get deep into the network, this type of compression will focus into some kind of more specialized architectures or elements that you find in the images. So we will see this, but normally in deep learning, for example, when you analyze images, the first layers tend to identify from an image things like more, how to say, generic or abstract, like borders. Then you start detecting shapes. Then you start detecting, by mixing shapes, figures and stuff like that. So this is how the overall deep learning works and the whole philosophy behind this. The interesting thing is that we are not really sure why. We believe that these are the reasons of why these things work, but they work damn well in many real-world applications. So what happens with deep learning is that the performance that we were getting was so astonishing good that we didn't stop, or we didn't have enough time to stop to understand why they were performing so good. And now, many years after this, like 15 years after that, we start realizing that many of the things that we are actually doing, they provide very good results, but are stopping further developments. And yeah, I mean, this is part of the overall philosophy. As we move very fast, and yeah, at some point we realized that we were moving in wrong directions. But okay, this is basically the overall thing. What's changed in the whole thing is that in the past, we had this idea of having multiple layers. But what we have now is that we understand how to train many layer networks. Because the problem of training many layer networks is that it's difficult to set all these parameters. Normally, when you train a model training means training all the empty, or let's say free parameters of the model in such a way that it will, given one input, put at the output the desired output that you want. For example, in a classification task, you know what it is and so on. So you set all the weights of the model, whatever the model is, and you achieve your training, right? When you are having these kind of very deep architectures, it was very difficult to set all these features, and suddenly we realized how to make it work. Some interesting things of deep learning. I will explain you how we do the learning, but some things that are very interesting about deep learning is that deep learning, it's super eager in data. So in order to use deep learning, you must use big data. If you use deep learning with small amounts of data, you are doing something that, I mean, it's completely wrong. It will be biased. It will provide you, for the specific data you have, maybe something good, but will be difficult to generalize. So small data, go to shallow learning, expert features, that's it. If you want to go to deep learning, be sure that you have significant amount of data so that you can really turn your deep learning model into something that works. But the cool thing of deep learning is that for most learning algorithms in shallow learning, there is a kind of saturation effect with data. And the more data, in some cases, the more data that you feed to the training will not improve your performance. So the model saturates, and even if you put more data to train, it will not improve. The thing of deep learning is that it still improves performance as you give more data, because the more complex the architecture is and the more data you put inside the training, the more you can fine-tune all these parameters so that at the end of the day, this type of architecture really mimics what that data is telling. But if that data is telling you everything because it's huge, at the end of the day, it will be like, imagine the following. You will overfeed your model to some data that actually the data describes everything. So that would be like extreme case to think about this. But the interesting, cool thing is that in deep learning, the more data you have, the performance always improves. And of course, I mean, why now we have deep data? As I was saying, we have the data, we have the computational power to do it, and based on these two things, we can really provide good solutions. What you see here is that, and now thinking in a more generic way, deep learning is about having big data. And having big data is not for everyone. So the problem of deep learning is that it's completely, let's say, in a social idea of the future or the development of technology, deep learning is actually putting the power into small hands. It's putting the power into those that actually have access to big data. So if you now think about just the competition between China and US in the AI domain, both China and US have access to strong amount of data. In Europe, unfortunately, we don't have that. Why? Because we don't have the applications. Let's say in Europe, develop all the applications that we use. So in those applications, you have all the data. In China, they have similar old applications and they can control that data. So they also have that data. In Europe, basically, we have nothing. Or for us, it's a bit more difficult. So in this race of AI, yeah, if you don't have data, it's very difficult to advance. Or at least we have to go to these other ideas of generative models and generate data and go back to these ideas of modeling and so on. But okay, just to say deep learning, the more data, the better, and progress in lots of fields, it's something crazy. This is what I say basically, so I will skip it. Why deep learning? And as we saw, the difference in deep learning with respect to shallow learning and the ideas of avoiding having to do feature engineering and so on. Of course, we will be talking about supervised learning, but deep learning can be used also in unsupervised manners. It depends on the architecture and depends on the type of application you want to do. Let's go back before going exactly into deep learning to the basics of what a neuron is. Okay, let me just say, from time to time, I just check the chat. Okay, fine. So, as I was saying, the idea here was to copy a natural brain neuron by developing this kind of artificial neurons. So in every neural network that you see around, deep learning, whatever, the basic element, the neuron, it's something similar to this. So basically, there are what we call the different inputs to this type of neuron. The inputs are basically weighted by some scalar weights. So imagine here the input are the x. So imagine we have a vector that is x0, x1, x2. So you have three inputs. And these inputs, actually, they go through, each of them, through a specific weight. The weight mimics the synapse between the previous neuron, because let's say the input to a neuron is the output of the previous neuron, right? So if you have this x0 coming from another neuron, and there is a weight there that is w0, what inputs to the second neuron is the w0 times x0. And this is a kind of reflecting the synapses between that neuron and this one. Because if that weight is very small, then whatever comes out, this x0 will be turned to 0. If that weight is very high, then this x0 will be empowered, and this means that it has a more relevant information. So you have all these weights. What happens inside the neuron is that there is basically a summing function, which basically just is a sum of all the inputs. So you see there is the summing of the inputs that are the weights multiplied by the outputs of the previous layer. There is one free parameter that we call the bias, that is this b, that is added to the summing function. Okay? And then what we have at the output is what we call an activation function. So basically what we do is that we compute this summing and we apply a function f at this, and this is what we copy at the output. And that's it. This is actually the basis of a neural network, and this is actually what you have to understand to say, okay, whenever I want to learn a neural network, what you have to configure are, or when you say training a network means setting these weights, W0, W1, and W2, and setting the bias, B. So for each of these neurons, you have to set all the weights and the bias. And that's it. So, I mean, sounds easy, of course, then it's very difficult to set it. But this is exactly what you do when you want to train a neural network. When it comes to the activation functions, of course, different activation functions will have a complete different impact, because the activation functions means how the input-output actually are correlated. So you have lots of different activation functions. Here you have some examples, like a sigmoid function. One of the most popular one is that ReLU function, that basically what it does is that for whatever output that it's negative, turns it to 0, basically, and at the output, if it's a positive value, just copies that value. This what does actually is introduces a high non-linearity, and if you introduce lots of non-linearities into your model, you make it potentially much more expressive. So this is why the ReLU function sometimes is very much used. In order to avoid killing the output when the output is negative, you can use a leaky ReLU function that actually, instead of putting it to 0, puts it to a smaller number. We will see, because there are some limitations that I will not be able to explain, but yeah, you don't want some things to be to go very deep to infinite numbers or to 0, because when you are training this, you do it by backpropagation, and you will be doing some kind of derivatives propagation, and you want to basically avoid some problems of that. But these are details that are there. But this is basically what we have in neural networks. This was just a kind of comparison of neural networks and the human brain. I already said this, so it's just to say that, yeah, we are still trying to understand how the brain works, so we are very far from that. Still, what I wanted to see from here that is interesting is that till the day I was doing these slides, one of the biggest deep neural network was having in the order of, okay, here is not the number, but okay, the ResNet 152, it has something in the order of, I don't remember now the number of neurons, but it has something like 60 million of connections. Okay, probably you could try to extrapolate from there. Whereas the human brain has in the order of 100 billion neurons and 1,000 trillion synapses. So the difference on these things is huge, is super huge. But what we will see at the end of the presentation is that nowadays we have deep learning models. I guess that maybe in natural language processing, you might have heard of some new models, this GPT from OpenAI, that are doing really interesting things. And they have in the order of 200 billion free parameters to calibrate. So you have a deep architecture with 200 billion parameters to train by training. So just imagine how complex these networks are becoming. But yeah, in any case, we are very far from the brain. And the most fantastic thing about the human brain as compared to this is the brain can do millions better than this in some specific cases, but without needing to consume so much energy. Because everything that is deep learning, you need superclusters. Without a huge cluster and huge data, so pay the bill because it will be expensive to do that, you will be able to build your models. But in the human brain, it's something that works, I mean, very far from here. A neural kind of things that I was saying about different hierarchies of data. Because I think that they are very simple to understand, because this is another thing of why the field of artificial intelligence is very successful. Humans, we are more interested in those things because we understand them. For example, image processing can be understood by my mother. I can explain my mother detecting a dog and a cat, but I cannot explain my mother detecting because of certain bytes. So it's much more popular, I would say. So imagine that we have this application that you want to classify numbers. Okay, so you have this image that it's a number, you have these pixels. How this learning of data representation works. So imagine what I will do here is that I will grab. Remember that I was saying that you have to decide on some way of how to input this to the network. Let's input to this network all the rows of this picture. I will put them all together, and this will form the input of my neural network. Right? So for simplicity, I put as input the force, and let's assume that those are the inputs, and they are connected at some point to this neuron. Okay, then all these lines, they correspond to the weights. In red, you have something that is a strong weight, so imagine a number that is high, and the other lines are basically weights that are basically 0, so something that is not very much connected. So if you consider this model, right, this neuron detect activation whenever it sees an horizontal line in the top row of the input image. Why? Because the way I just put the input there, you see that the first thing that is highly connected to the second one is just the pixels of the first row. And whenever there is some kind of dark area there, this will actually, assuming that the dark elements here are ones and the white are zeros, this will highly react to this kind of black dots or dark areas on the first horizontal line of the row. So this means that the model here, this type of self-learning of the representation done by the network, will be done by, okay, how these weights are basically discovered. Imagine that now the training of the network gives me this other type of weights. So if the weights are set like this, just considering the first three weights, the first three pixels of each row, this type of activation or this type of neuron will basically be able to detect or have strong activation whenever there is a strong area in the top left corner of the input image. All the rest will be basically ignored. So if you just now can see how this works in a more generic way, whenever I'm training my model, depending on how the architecture it is, how these connections are set, and I start training by saying, okay, I put this in the input and I tell that at the output it has to be a number 9, all the different hierarchies of these, because remember that these are then interconnected, start learning things that appear at different areas of the image. So for example, in this first layer, with this simple thing, what you will detect is like borders or specific areas or let's say stuff like that. Of course, then the overall idea is to make it a bit more complex because as I am saying it now, it will just react to, for example, a number 9 that appears with borders in the corners or stuff like that. The interesting thing is that we can improve this by having convolutional networks. But this is the basic idea of how to explain data representation learning. Data representation learning is nothing but setting those weights, and depending how these weights are set by the training algorithm will be what the algorithm is basically detecting. So it's very simple to understand. There is no magic, and yeah, that's it. As I was saying, when you're going to train a neural network, the idea of training a neural network is basically to define a loss function that tells you at the output. We train a neural network or a model to provide at the output something that we are, let's say, assuming supervised approach, that we are telling the ground truth to the model. So what happens is that we have, for example, in this case, we have all as input all the pixels of this number 9, and at the output we tell the architecture this is a 9. So in this case, what we have is in this type of, let's assume this is a classification and we are classifying numbers from 0 to 9. We can define a loss function, and the loss function will basically tell me if I am very close to the target, let's say, to put for the input the correct output or not. And based on that, I will try to propagate that information through all the training phase to try to set the parameters in such a way that the overall, let's say, error is minimized. So basically, training is nothing but an optimization problem in which I have to set all the free parameters of the neural network, that in this case are the weights and the bias, in such a way that the overall, let's say, performance or the overall, let's say, loss function is minimized. Simple. Or let's say, what we know from the past about optimizing networks. Of course, in order to optimize a function, remember, optimizing a function, there are many ways to optimize functions. The optimizer, these are called, the optimization you use defines what in deep learning it's called the optimizer or the optimization function. It also defines the way that your function will be, let's say, your weights will be learned. So depending on the architecture, you can use different, let's say, and they will provide different results. I will explain you here the gradient descent. Stochastic gradient descent, you know, you saw it, the fact that you don't remember, simple. What you do is that is the of your function. What you will try to do is to the direct. Remember, what we want to do is imagine here in this function we have to minimize of let's say we want to minimize the cost. So what you want to do is to find the place where the derivative of the cost is 0. Computing the gradient is very difficult because the gradient you don't know it. Because in order to compute the gradient, you must know the function. And here we don't know it. So what you normally do, you remember this Jacobian build the based on the parameters, you can build the derivative of the loss function, and you can start moving into the direction that decreases the most. So it's the direction where the derivative is mostly negative, or the highest negative value, and you start moving in that direction. So basically, this is what it means to do stochastic gradient descent. And now how do we apply this to the neural network? So remember that in the neural network, what we want to set as what we want to achieve by the optimization is to set all these parameters. So the parameters that we are, remember the weights and the bias, let's call them theta here. And what we are going to do is that in order to optimize these theta parameters, we are going to do an iterative process in which the theta are computed based on this, remember, the derivative of the loss function. So basically at each step, what we are going to do is to consider the new, let's say at each step of the training, we have a set, we obtain a set of parameters. And this set of parameters, what we can do is to try to keep improving them by just, once again, feeding more data. With that data, compute again the derivative of this loss function all over the network. And once again, updating the weights in such a way that I'm moving towards this type of minimum. What happens is that computing the analytical expression of the gradient is straightforward. It's what we have here. But numerically evaluating the gradient is computationally very expensive in the way this gradient function it is. So the idea of backpropagation, and this is actually it's very simple and it's very interesting, is to use this way of how can I actually these partial derivatives in such a way that I start computing from the loss function. The loss function is actually a function that comes from the output of the last layer of the neural network, which actually depends on the inputs of, on the outputs of the previous layer. So there is this kind of chain in which the output depends on the previous outputs. And in order to compute actually this derivative of the loss function, we can use the chain rule. You remember the chain rule? Actually, the chain rule basically tells me that, for example, here I have how to basically compute this derivative, yes, of the loss function in a kind of propagation to the back. That this function or this neural network neuron source is the last one of my architecture. I will compute the derivative of the loss function with respect to the output of this. And actually, in order to compute this, if I use the chain rule, I can say that this derivative is actually equal, or let's say I will use it in the computation of the derivatives of the previous layer functions. Because let's say in the inputs of this function, it's derivative of the loss function with respect to the output of that neuron, in this case with seed, and I can just use this kind of chain rule. So I compute it once and I propagate to the back. So this is actually why it's called backpropagation, because output, that is what you have, the loss function, and then by using this chain rule, you start propagate these derivatives towards the full architecture, towards the input. At the end of this, what you get is actually a full estimation, yes, of this kind of gradient of the loss function with respect to the input, and based on that, you can give one new step towards the part where this function minimizes the most. So, I mean, grosso modo, this is basically recalling the things that you've seen in the past, but it's also, again, it's very simple concepts. There is nothing complex here that it's just a derivative. It's just that in order to compute the derivatives for all these kind of functions, you do it in this way and works quite well. The thing is, okay, how often you will do this derivative? How often you will update weights? And what you do here actually is to train your data based on what we call epochs. So an epoch of a training approach represents one iteration over the entire training data. So imagine that you have a training data of size m. Once you feed all this data to your neural network, you will compute the value of the loss function, okay? And for that, you will have a full chain of these derivatives computed, and you will have an optimization of the parameters, and you have the value of those parameters after the first epoch of training. What you will do after that is that you will use, again, all your data, you feed it again, you compute the function, and again, you start moving in this direction. So normally when you're training an algorithm, you will run the same data many times, so you will do many epochs to train your data. But the thing is that when this data is too big, when a full epoch of data with this size is too big, it's not very efficient to do it that way, because every time you will feed all the data will take lots of time, and computing derivative will take lots of time. So what we normally do is that we compute this in batches. So if that is too big, we split it in batches, and what we do there is we feed small batches of data, and at each of these batches steps, I will update my weights. Okay? Of course, there are two extreme cases. There is the what we call the batch gradient descent, is when you basically consider as batch all the training data. So if you say that in one epoch you have size m input data, and you use all that data to build your batch, then means that each epoch corresponds to the training on, let's say, to doing a training iteration on all the data time and time. If you then do something that is called online training, instead of feeding all the full data at once, you will just feed one sample per time. So one input per time. So you just grab one sample data, you put it there, you go to the end of the network, you compute the whole derivatives and so on. And okay, this is super slowly, and you will give very small steps on the optimization. But okay, at every iteration, it goes very fast because it's only one sample. What we do in the practice is that we use mini batches. So mini batches is that instead of using all the data, or instead of using only per one sample data, we take something in the middle. So we split our whole data in mini batches, and yeah, we just train on all these things. So this is basically what we have when we do the optimization of the cost function versus the number of iterations. In the left side, this is a batch gradient descent. So we take all the data at each of the iterations. So you see that the optimization gives you a very stable optimization, because every time you move, given that you fed lots of data, the computation of the derivative is very strong. But at the end of the day, this goes very slowly, whereas the mini batch is much more noisy. But at the end of the day, you also converge to what you are expecting. So in the literature, and this is one expert, Jan LeCun, says that, let's say, it's important to always use mini batches, and these mini batches have to be small. So for example, in most of the applications, they use mini batches that are no larger of 32 samples, only 32, right? Regularization. One of the things that when we are doing this optimization is when to stop this minimization, yeah, right? Because you can just say, okay, I will stop when the, let's say, cost function reduces to 0. But yeah, actually, if you do that, you will probably be overfitting your data, your model to the data that you are seeing. So there are different type of techniques that are used for what we call regularization, that is to counterbalance overfitting problems. So early stopping is the most traditional one, when what you will do is that after each epoch of training, you will train your, you will apply your trained model into a completely different data set, and you will see the error that you get there. And you will get something like these curves, like you continue training, and in the training data, of course, the error keeps reducing, but in this validation data that was separated, at some point, you will see that the error starts increasing. So here what it means is that the model started overfitting because in the training data, you're improving the results, but not in the validation set. Okay, so this is a way to say, okay, I will stop there the training, but there are other techniques like dropout. Dropout is this technique that I was telling you that you will basically try to some sort of saying average multiple models by basically adding layers in which you will, at each iteration step, drop some neurons randomly in such a way that the architecture that you're training slightly changes time after time. In such a way, they have shown that it's also a very good way to achieve good optimization and regularization. But there are many also hints and approaches to do this. Other approaches that help you in computing these derivates and to actually improve the chances of achieving a good training is to do data normalization. So data normalization is that the data that you're feeding to the model, imagine that you have some inputs that you will normalize. At each of the hidden layers that you are passing, it will also change dramatically based on the number of the value of the weights and of the activation functions. So what it is recommended is that you do, on the one hand, batch normalization. So every time you have some input data, you normalize the data, but also at each step from one layer to the other one, you add some layers that renormalize the data in such a way that you always try to keep, let's say, the data without going into extreme cases, like too big values or values that are too close to zero. Why that? Because when you take derivatives, of course, they will perform very bad if they are close to zero or close to something very high. Last thing, we are approaching the end, but yeah, I mean, last thing I wanted to show you is about, okay, how now all this boils down to convolutional networks. So a convolutional network is just what I showed you before, but instead of using specific links between neurons, we use a kind of different structure that is a filter. So basically, a convolutional neural network is a sequence of different convolution layers with some activation functions and some other layers that are called pooling layers that are all put together, as many as you want. But basically, what they achieve is specialization of the data, and then you connect them with some other layers that, at the end of the day, helps you in better achieving the overall goal of the training. But in a nutshell, what you want to do is something like this. You want to have some sort of architecture that at the first layers we detect, in the same way we showed you before with the numbers, will detect or let's say more abstract information. So for example, from the image you will start detecting things that are like borders. Then you will start detecting things that are more complex because they take as input part of these borders and they mix them to create figures or to create shapes. And then these things will be recreated or mixed together to create things like, for example, faces or cars or stuff like that. So that's the overall idea of the convolutional network. How actually the convolutional network works? Something like this. In a nutshell, instead of having these weights, what we have now to set are these, let's use the pointer, we have, instead of having now weights, what we have to set are these feature detectors. So these feature detectors are basically just a kind of filter that you apply to your image that we basically have a sort of activation in the sense that whenever one of these number matches the number that it's in there, okay, it depends if it's a 0 or a 1, will basically count a positive additive value, and if it's not matching, will count 0. And you will do a kind of summing of this information in this way. And here, this, let me show you something more graphical, how this works. So imagine here you have an image that is this green 1, 1, 1, 0, whatever, and I have this filter that is this green thing, that is this 1, 0, 1, 0, 1, 1. What you basically do is that you multiply this filter by the values of the things that you are analyzing, in this case, the inputs of the feature, and you start for each of the, let's say, areas where you're placing the feature, you're obtaining a number that multiplications in here is nothing but this old term that you saw also at the university that is doing a convolution. So basically, you are basically applying a feature detector on top of these different pixels, and you are computing a kind of output that is the output of that type of filter going through the image. So what happens here is the following. Instead of, in the convolutional network, instead of having to learn the weights or the connection between neurons at some layer and the others, what you have to learn is this feature detector. So the feature detectors, these numbers that are here, zeros, one, or whatever they are, you have to discover them. So the training at the end of the day is to see what are these things. Okay, at the very beginning will be zeros and ones, because if you see it a bit carefully, they will react in the same way we're showing to pixels that are activated or not. But then they can be things that react to numbers like fours or threes or whatever that came in the second layer. Okay? What comes that basically this convolutional layer that you are computing, let's go back to this convolutional layer that is applying this feature detector gives you as output what we call an activation map. An activation map is a new matrix, in this case, that are these, again, this kind of, in this case, is the pink values that you are getting. What you do then is that these values form the new layer of the second part of the network. And what you will apply on top of this is a new feature detector that you will apply to this, and like this, you will just basically perform, let's say, deeper analysis on the values themselves. The thing is that you can combine the convolutional layers with different activation functions. So instead of just applying, for example, here the filter is just doing these multiplications, and at the output you are having the summing. You remember in the neurons, instead of just copying the summing, you pass it through an activation function. You can do the same here, and the activation map that you will create at the output will be based, or the number you get is based on the activation function that you're applying to that convolution. Again, here you can use whatever, the ReLU and so on. The interesting thing here is the following, is that depending on the number of filters that you want to learn, the size of the filters, because here in this picture I was having, it's only one filter of size 3 by 3, okay? And depending on what we call the stride, is how do I apply this filter all over the picture? I could decide to just shift the filter one sample at a time, but I could do something that shifts the filter, let's say, twice, two samples at a time, and so on. Depending on these three parameters, the architecture or the size of the next layer will be decided. Because, of course, if you have, let's say, a bigger stride, then let's say the activation map that you achieve is smaller. If you, for each filter that you will apply, you will have a different activation map. And depending on the size of the filter as well, you will have a different size of the second layer. So basically what you are doing here is like this convolution is by passing some features that will detect some stuff in the image. By combining this, many of these layers, you have what we call a convolutional layer, a convolutional network. The convolutional network actually, instead of just adding these detection filters, you actually add some other layers that are called pooling layers. The pooling layers are just some ways to drastically reduce the size of the network by basically dropping information. So they have basically a pooling layer. It's a way to condense the information in some matrix into something that is smaller. So there are different approaches. Imagine this approach that is very popular. It's called max pooling. So the max pooling here, for example, if I have a 2x2 max pooling approach, will basically grab this input that is this 4x4 matrix. Imagine that this 4x4 matrix is the output of the previous step. A max pooling, what it does is, if you have a filter of size 2x2, it keeps in each of these 2x2 blocks, it keeps the maximum value. So in the first 4 blocks, the maximum value is 100. In the second one is 184, and like this. You can also use average pooling that you keep for the next stage, the average of all those values. What you're achieving here is that using this max pooling layer, you're drastically reducing the size of the activation function, because here you have, let's say, the output was 4x4, and here the output is 2x2. So what you're doing here is that reduce the size of your architecture. At the end, what you do is, let's say, so basically the convolutional network is only that. Convolution layer, pooling layer, convolution layer, pooling layer, and as many as you want. Then you want to translate this into some sort of classification. So you have what is called a flattening layer that is just grabbing the pool, so the activation map that they were these matrices, and you put them in a vectorial fashion. So you just copy, for example, in this case, all the rows into a single vector. And this you just then input it into a standard neural network. So what you do after the flattening is that you basically, here, you remember, we have the input image, convolutional layer, pooling layer. You just, at the end, you put it into a traditional neural network, and that's it. This is a convolutional neural network that is the basis of, let's say, deep learning, big, outstanding performance. At the end, of course, you can do, for example, you can add, let's say, if, for example, in this neural network, fully connected, you want to have an output that corresponds to probabilities, you can add other popular layers like a softmax layer. There is just a softmax function that ensures you that the values at the outputs all together, they add up to 1, so that it is a probability. But that's it. I mean, what I show you now, of course, there are things that you might not have understood because there are some small details, but it's very simple. So deep learning shown like this, it's nothing else than this. And all these type of things at the end is what has created all this type of history of models that are performing better and better time after time. What happens is that convolutional networks, they are very good because they can detect different elements in different sizes or let's say positions, but convolutional networks, they might fail a lot because they lose these max pooling layers, they lose lots of spatial information. So I have this example for you. Imagine this face. So this face, it's not a face. It's just one circle surrounded there with a shape of a face, but it has 2 eyes, 1 nose, and 1 mouth, but it's not a human person, right? If you pass it through a convolutional network to detect faces, of course, it will tell you that this is a face. Why? Because it detects the shape of a face with a probability of 70%. It detects each eye with a probability of 90%, a nose, and a mouth. So its probability, it's 95% sure that this is a face. But of course, we know that it's not a face. And the problem is that the convolutional neural networks, they lose lots of spatial location information because of the max pooling. So new evolutions of this is what we call the CAPS-nets. Capsule networks, basically what they try to do is to encode the probability of an object being present in, let's say, different context, or the spatial information is also put into the model. So by doing that, what we are achieving is that instead of saying that this is a specific eye, we will have information like this is an eye that is next to this other eye, or this eye is at the right side of this other eye. And this information you can actually put it within the neural network. For example, something very simple would be like, instead of just encoding the pixels of the image, you can put this type of orientation and size of the different elements that are detected. And by doing this, you can actually improve the performance of these type of convolutional networks to actually be able to understand what is called the context. Why I wanted to mention capsule networks is that there are new evolutions. Let's say capsule networks are research and they never provided, let's say, super powerful results. But convolutional networks, as we know them, might be close to the end because there is a new, let's say, unfortunately, I don't know if I will have time to show you, but there is a new approach that has born, let's say, in the last 2 or 3 years that is called transformers architectures. So in the natural language processing field, there are a specific type of architectures that they are trying to completely remove the needs of convolutional networks, or in the case of natural language, recursive neural networks. I will not go into the specific details, but they are very good actually to model sequential data. So transformers, if you know this kind of BERT models that Google uses to optimize a search or do translation, just think about why Google Translate or Bing Translator or all these models are performing so well in recent years. Is because they are improving natural language processing by these type of things, by transformers, attention mechanism, and these type of things. The cool thing is that now we are using these type of architectures to also analyze images. And the thing is that there is now a new paper in ICLR 2021, it's currently under evaluation, in which they are using this type of natural language processing approaches to actually process images, achieving much better results. So in the other sets of slides, you have some ideas of what these things are, but I just wanted to show you that deep learning is about neural networks. When we talk about deep learning, convolutional neural networks are or were the king of deep learning, but there are still now new improvements that are coming, and what we have seen might change very rapidly. So just to give you an idea of how all these things are going. Okay, this is the end of this chapter. Unfortunately, I don't have time to show you the last chapter, but I will just show you from the last chapter one slide that is the contents on this chapter. So in this chapter, I wanted to put other relevant topics related to learning. Again, this is related to learning in general fields, so it's much more to image processing and to natural language processing. But what I wanted for you to see here is that all these things can be directly applied and are being applied into networking problems. And there are many interesting things that you can dig into to actually do your research. So things that I wanted to talk to you, it's about, okay, I've shown you convolutional neural networks. I told you about recurrent neural networks. Language processing. And these are the things that at the end of the day are starting to be dropped by these new mechanisms like attention and transformer architectures. There is a whole field that I didn't talk about that is reinforcement learning. I think reinforcement learning for our domain is super important because imagine that in networking, we have lots of closed loop information, right? And when we have closed loop information, we have this kind of loop that is needed in the reinforcement learning. In reinforcement learning, it's not supervised or unsupervised, but you learn by just doing some action and seeing what comes out of that as an output. Based on that, you can say if the output was good or the output was bad, you can move into certain directions. So I think that reinforcement learning, and in particular deep reinforcement learning, that it's using the power of deep learning to explore the different spaces or the different, let's say, areas where you can move or the different policies is super popular. So go into that. Generative adversarial networks, this opens the door to this other field that it's about generative models in which you can basically now use deep learning models and you can use these type of approaches to learn very complex data distributions without even having a clue of how these data distributions are. Data distributions are there is a whole field in statistics that it's learning distributions. So you have learning by kernels. There are many different ways that you can do it. But when you want to learn a complex distribution, when there are many joint distributions and so on, all these methods, they tend to fail. And in a fully data-driven approach, generative adversarial networks are extremely good for that. So pay a look into that. Graph neural networks, yes, this area graph neural networks, I think could be for us networking people a killing bullet, so a silver bullet to what we do, because graph neural networks are just deep learning models that are adapted to work on top of graph data. And of course, there are many problems where data is much better explained or represented as graphs. Where is that? Well, in networking, graphs are extremely good because they describe many of the things we do. So I would say that go into graph neural networks. Graph neural networks are also becoming super popular. In the last 3 years, in conferences like NeurIPS or ICLR, they are becoming really one of the top elements that are appearing. They are a huge domain itself, but also very good to go there. 3 more things. Adversarial learning. The cool thing of adversarial learning is that this idea that I told you about trying to fool a system or trying to have data that is contaminated to actually fool the models and so on, this actually opens the door to the fragility of artificial intelligence in general. Artificial intelligence is very, or let's say not very, but it's easy to fool. You can train a model, you can put it there, and even if I don't know the intrinsics of the model, I can try to fool it in kind of different ways. And the adversarial learning is a whole field, and it's good that they discover, they realize early enough that whenever you do machine learning, there is a lot about the security of the machine learning model. And it's very important, actually, to understand this, not only for the security in terms of someone wanting to attack it, but also in the security about the robustness of the model. For example, for self-driving cars, we have seen that a car can actually be fooled by some stop signs that they have some graffitis on top of that. So what we discover is that there are some type of modifications in the input data that can totally fool the most common, one of the big areas of machine learning, and for networks, it's tough for do is that part of that learning you can use it to actually apply it into a similar but different problem. For example, in the kind of image processing, what they have seen is that they could train some convolutional networks to detect faces and use the first type of layers that were able to detect, let's say, edges, to then actually use them as pre-trained layers into an application that was able to detect cars. But the thing is that in that application, they had much less training data. So instead of training the whole neural network, they used the first layers already pre-trained because they were trained into different applications in much more data. But these initial layers were, let's say, abstract enough to be able to, let's say, reuse them in different architectures. So the idea of transfer learning is that we can do similar stuff in networking. Whenever you have lots of data, you can try to build some models where you can stop up to certain levels where you say, okay, what the model is learning here is abstract enough, so that I can then reuse it into some other applications where I might have less data, but there I would definitely improve my results. And last but not least is about automated machine learning. As you've seen in the presentation, anything that comes with machine learning, and let's say deep learning in general, is full of decisions that the end user has to take. Which is the architecture? How many layers? How many activation functions? Which activation function? Which type of batch size? I mean, you have so many things to decide when you're going to do a deep learning architecture or when you're going to do machine learning that it's actually a cumbersome thing to do. So the expertise sometimes is actually on how to combine these things based on what you already know. There's a whole field that it's called automated machine learning that tries to automate these decisions. So basically, automated machine learning is about doing some sort of meta learning in which what you try to do is, given some input data and given one specific task, the whole approach tries to recommend you which is the best architecture that you can use, which are the best optimization algorithms that you can use, and so on and so forth. So AutoML is also a super powerful approach. It's also coming very strongly. And again, for us, when we want to jump into this, it's very strongly, let's say, recommended to pay a look. So I would say from here, very strong for you to know that besides recurrent neural networks and convolutional neural networks, now the future is coming into transformers. So we will soon drop them, everything, we will drop them into these things. So pay a look, start looking what attention mechanisms transformers are. And then reinforcement learning, graph neural networks. Thanks for your attention. Sorry for being such a long thing. I mean, the training is 3 hours, but I think that face-to-face 3 hours are much better digestible. But again, really, thanks a lot for being there. And as I said before, please, if you're interested in whatever, drop me a line with your email and we can discuss. I mean, feel free. Last, if you're a student, don't forget to fill in the Google form. Google form that it's here. I just share it again, whenever it is here. And yeah, fill in that. And that's it. The end. Thanks.
Thank you, Pedro, for really providing this interesting tutorial. And I don't know, do we have still some time for questions? Any questions from students, attendees? No, even in.
This is Andre Bondi. I have a question.
Go ahead.
When I've looked at machine learning presentations, I'm sorry, I didn't put my phones on. I was listening with a loudspeaker. When I've been, as I was listening to this presentation, when I've listened to other presentations, I was wondering how one takes the underlying distribution of the variables whose data you're collecting into account. Because on the one hand, you're saying that for deep learning, you need to have a large number of samples. On the other hand, if the underlying distribution is Cauchy in at least one of the dimensions, then taking a large number of samples isn't going to do you any good. And I'm wondering if there's an implicit assumption here that the large number laws apply.
No, I mean, it's a very good question. Actually, if you know already things, let's say in deep learning, normally you don't make any assumptions of the distribution of your data. So
right.
it's more generic. So this is why you say your whole problem is described by huge amounts of data. And the more data you have, the better your system will learn what is actually happening in the background. But of course, there are different architectures that if you know some distributions of your data, you can actually plug into the model that information to really improve, let's say, the overall performance. Because let's say in some cases, if you already know the distribution, maybe as you are saying, using more data will not change anything, and you might use a different model that is actually tailored for that type of distribution data. So in general, when we talk about deep learning, we never make assumptions about the distributions of the data. And this is the beauty of the thing, because you can easily do it in these kind of data-driven approaches. When you know things about your input data, then in some cases, going to shallow learning. In shallow learning, there are models that they make assumptions on the input data. For example, models that could be just like, let's say, things to analyze, for example, compressing the data, like doing PCA analysis and so on, they do strong assumptions on the distribution of the data. For example, PCA assumes that the data lives in a linear manifold. So if you know that your data lives in some linear spaces, you can use some other techniques, and of course, no necessary to do all these things. In general, the deep learning works well when you have complex systems where you cannot really, from the complex system, guess the distributions, and still, with these approaches, you can achieve good results. But totally, I mean, when you get information, there are many approaches that you can actually plug it in.
Does the same hold for classification problems?
Yes, definitely. I mean, in this actually, you can actually see it in the, let's say, in the other slides where I talk about shallow learning. I do different approaches, and the first one I consider is a very statistical based. And if, for example, you have the a priori distributions of the classes that you want to classify, you can build let's say, a very simple classifier in which you take into account the a priori distributions. Because let's take an example. If you're classifying between, let's say, sharks and dinosaurs in let's say, in the ocean, the a priori probabilities of dinosaurs is probably 0 or something close to 0, because we don't have dinosaurs at all. And yeah, I mean, the chances of having sharks are much higher. So that you can plug it into your model. But in general, yes, all the information you can have on your data can be used. And the more information you have on the input, the less you have to go into the deep world. Because the deep world, what they try to do is to learn these things. But as I said, the shallow learning is the extreme case of saying, okay, I know my data, I know the features, forget about deep learning. Definitely.
Okay, thank you very much.
Thanks to you. So yeah, I mean, probably difficult to make questions after so many time, but yeah, again, if at some point when you are reviewing the slides, something comes to your mind and so on. I mean, it's a pity that, yeah, in the 3 hours, it's a bit difficult to go through all these other relevant topics and stuff like that. But I ask you, please, when you have some time, to check these other slides. And if there are specific topics that you are interested and you would like some pointers, just drop me a line, and yeah, it would be a pleasure to guide you.
Yes. Yeah, I don't know if you mentioned that there is a Slack channel related to the tutorial. So, and
No.
I would suggest, yeah, there is a Slack channel, and actually this will be active even after the conference will end. So, I would suggest to register to the channel in a way that I mean everyone can see the comments and the questions and so on. So, would be. Yeah, these are the slides. You put the link of the slides I just put in the website because I was starting the other session, so I was not able to put it earlier. I don't know if is there any other questions?
Sorry, no. I was just thinking on a. They were asking me for a paper on graph neural network, so I do it now.
Okay.
No, but go on.
It's all from my side. I mean, so we can.
Good. Okay. I mean, if there are no more questions, again, I thank you. And yeah, I mean, as usual, I enjoy talking about these things much more face to face, where I can see your reactions and we can talk more. But yeah, I think that we are doing quite well with the remote things, and hopefully we will see each other face to face sooner than later.
Yeah, sooner or later, maybe the next year in Milan, because we will. I mean, we hope to host physically the conference the next year.
Definitely.
Yeah.
But yeah, thanks to everybody there, and yeah, stay safe, and yeah, good luck. And of course, again, whatever you might want, drop me a line. You have my email there, and that's it.
Yes, and thank you a lot, Pedro. Thanks really for this nice.
Pleasure. Really, it's always nice.
Okay, thank you. So bye everybody, and I hope to see you again the next days during the conference.